A modern jetliner like the Boeing 777 is more than just wings and engines. It is a complex, self-contained environment. It must create its own comfortable atmosphere at altitudes where the outside air is too thin and cold. To achieve this, the aircraft relies on a constant supply of hot, compressed air. This vital resource is known as bleed air. It is not some extra fluid carried on board. Instead, it's air bled directly from the turbofan engines under the wings. This air is the lifeblood for several critical systems: pressurization, air conditioning packs, anti-ice heating for leading edges, and engine inlets. Without it, the cabin couldn't be pressurized. Flying at 37,000 feet would be impossible. The AC packs cool bleed air to a breathable temperature. Even engine starting often needs bleed air, and from the APU or a ground cart. Bleed sounds dramatic, but it's a controlled engineering process. To understand where bleed air comes from, you must first look inside a turbofan engine. An engine pulls in air and compresses it through a series of rotating blades, mixes it with fuel, and ignites it. The compressor is divided into stages, with pressure and temperature rising step by step. The 777 has two main bleed ports on the compressor. Think of them as two taps with distinct properties. The low stage port is at an intermediate stage. During climb and cruise, high power makes low stage air ample for the system. It runs packs, pressurization, and anti-ice. The high stage port sits deeper, nearer the hot core. Its air is much higher pressure and temperature, but tapping deeper air affects engine efficiency more. So the system uses low stage whenever possible. It's cooler, needs less pack cooling, and saves fuel. High stage stays in reserve for when low stage isn't enough. This elegant logic underpins the 777's automated pneumatics. The flight profile swings engine power from high to maximum in climb, to steady high power in cruise. But in descent, thrust is reduced toward idle. Slower compressors mean less compression per stage. Low stage bleed pressure begins to drop. On a long idle descent, it can fall below system minimums, yet pressurization, packs, and anti-ice may still be needed. The solution isn't to add thrust during descent. Instead, the system automatically selects a stronger source. That's how it handles the descent dilemma. Remember the pattern that follows. Low power yields low stage pressure. The aircraft compensates, automatically. Especially with anti-ice on, demand can be higher at low power. Yet the cabin experience remains steady. The Boeing 777 doesn't ask pilots to manage bleed sources. An automated high-stage valve handles the switch. It's a computer-controlled valve on the high-stage line. At high power, the valve stays shut. Low stage is preferred. Controllers continuously monitor the bleed manifold pressure. In descent, if pressure dips below a threshold, the controller commands the valve, and the high-stage valve opens. Hotter, higher pressure air floods the manifold. Manifold pressure snaps back to target. The switchover is seamless and entirely automatic. Packs and anti-ice continue to function normally. As thrust rises for approach, low stage pressure returns. The system then commands the high stage valve to close. It reverts to the more efficient low stage configuration. While the source selection is automatic, pilots are never in the dark. The AIR synoptic presents a clear schematic of the system. It shows the engines, the bleed ducts, the valves, and the packs. Pilots can see the high-stage valve status for each engine. Closed is typically a green, vertical line. During low-power descent, it changes to show open. It may rotate or change color to indicate flow. Ordinarily, seeing it open is a non-event. It's expected on long, idle descents, with anti-ice on, or during ground operations. If something goes wrong, ECAS posts a message. For example, a valve stuck open when it should be closed, or failing to open when commanded. Then the crew shifts to checklists and problem solving. Most of the time, it's just a quiet symbol doing its job. The 777's bleed logic distills to a simple rule: high thrust, low stage, low thrust, high stage. In climb and cruise, it uses the more efficient low stage bleed. In descent or on the ground, it switches to high stage to compensate. Defaulting to low stage conserves fuel and reduces thermal stress. High stage stands by, ready the instant it's needed. The cabin stays comfortable and pressurized throughout. The change from low stage to high stage and back is transparent. No jolt, no pressure change, no airflow interruption. On a long, quiet descent, imagine the computer sensing the shift, opening a small valve to draw hotter, higher pressure air. No pilot action required, just smart logic at work. It's why your 777 breathes differently on descent. quietly ensuring a safe, comfortable journey.